I started designing this preamp in late 2019, and it took about a year to go from the initial ideas to the finished preamp you see in the photos. I drew a lot of inspiration for the MC part of the design from Richard Lee's Duraglit Special, which in turn was based on Marshall Leach's 1978 transimpedance topology design. Going from the final circuit diagram to the completed preamplifier, including measurements and listing tests, took 3 proto-builds to get 100% correct, and the design was published in 2 parts in February and March of 2021 in Audio Express. This video is designed to accompany the written articles, which you can download for free at Audio Express. The links are up in the comments section below. This is a view of the completed preamplifier out of its housing. About 60 board sets have been sold as of October 2024. As far as I can tell, most of those have gone on to be built. Let's do a quick summary of the specs before we dive into the details. For MC inputs, the front end can be switched via dip switches on the rear of the unit to cater for 1 ohm to 40 ohm cartridge inputs, covering 100 microvolts through to 500 microvolts output. The dip switches pertaining to the MC inputs do not adjust the cartridge loading, but only the front end gain. I'll discuss the reasons why a little later on. For MM inputs, the unit will accept 1.5 through to about 10 millivolt inputs. This is a rear view of the preamp showing the MC and MM input receptacles, output and switches, allowing the gain and loading to be tailored for the source cartridges and line level preamp used. For both MC and MM inputs, the overload capability of the preamplifier is greater than 30 dB. The MM stage uses a single stage all active topology, so the overload capability, as with the MC input, holds over the entire audio band all the way out to 50 kHz. A little later on in the video, I'll explain why overload figures of 9 to 12 dB that you see on designs using active-passive topologies are nowhere near good enough for a high-fidelity phono stage. The X-Ultra MC-MM incorporates a system gain stage after the RIA stage, which allows the overall gain to be raised from 0 to 9 dB in 3 dB steps. This was done to cater for line preamps that still provide legacy 350 millivolt input sensitivity. So the preamp can be matched to legacy input sensitivity levels of about 350 millivolts by setting the system gain to 0 dB or plus 3 dB, or to modern 1 volt sensitivity line level inputs by setting the system gain to plus 6 or plus 9 dB. Following the system gain stage, the preamp has a rumble filter. This is permanently in circuit and features a minus 40 dB per decade slope below 20 Hz. A feature of the filter is that via a switch on the rear panel, the turnover frequency can be raised to 45 Hz. And I did this to address the very low frequency acoustic rumble evident in some older classical recordings where this is apparent. This noise arises because of air currents and large recording spaces that are picked up by the sensitive microphones. The total power draw of the preamplifier is about 2 watts, and the mains power supply is built into the unit. In the Audio Express articles, part 2, a set of measurements are discussed. Despite this being a conventional unbalanced input with an onboard mains supply, it is exceptionally quiet both in terms of thermal noise and mains hum. Let's take a look at the design constraints, the 2 types of transducer, moving coil and moving magnet, placed on the electronics. In a moving magnet phono preamplifier, there are 3 major noise sources to consider. The amplifier's input referred equivalent thermal noise voltage, its input referred noise current, and then the thermal noise of the resistive part of the cartridge. The industry standard load resistance for a moving magnet cartridge is 47K. At LF, the cartridge inductive reactance is low, and the 47K resistor is effectively bypassed or shunted by the 500 to 1.5K cartridge coil resistance. As frequency rises, the coil inductive reactance quickly rises so that in the top octave of the audio band, the 47K load resistor is being shunted by 15 to 20 k ohms from the cartridge inductance plus coil resistance. The overall result is that the amplifier noise current flowing through the shunted 47K load resistor plays a significant part in the overall noise performance, so it is important that amplifier topologies and input devices that feature very low noise current are used with moving magnet cartridges. For this reason, the X-Ultra MC-MM uses an ultra-low noise LSK389B JFET, or alternatively the TI JFE 2140 JFET. These devices feature wideband noise voltages of around 0.9 nanovolts per root hertz, but almost zero current noise, which means the noise current contribution is minimized. One of the reasons the NE5534A, a legacy 45-year-old op-amp, fares so well in the moving magnet phono amplifiers is that despite its quite high noise voltage of 3.5 nanovolts per root hertz, its input noise current is very low at 0.4 picoamps per root hertz, typical, and thus minimizes the noise current contribution when fed from a real-world inductive source like a moving magnet cartridge. For reference, a typical moving magnet cartridge of 1.3 k ohms coil resistance and 500 millihenries coil inductance, shunted by a 47k resistor, will generate around 3.1 microvolts over the audio band. This sets the flat response signal-to-noise ratio reference 5 millivolts to 64 dB. RIAA equalization frequency response shaping, however, means this figure is raised by 12 dB in a well-designed preamp, and these are unweighted figures. For moving coil transducers, the coil resistance usually lies between 3 ohms and 30 ohms, and the coil inductance between 25 microhenries and 100 microhenries, so the amplifier noise current discussed above plays little role in most cases. However, since the output of these transducers is very low at between 50 microvolts and 500 microvolts, minimizing the noise voltage is absolutely critical. The Xultra MC-MM input operates in a current injection mode, aka transimpedance stage, to achieve best-in-class noise performance, and we'll go on to discuss that in more detail later on in the video. This graph shows the amplifier noise comparison, so noise voltage and noise current considered for a range of popular low noise op-amps and the LSK 389 or JFE 2140 JFET. None of the op-amps are better than the discrete JFETs. Further, in the Xultra MM amplifier, the two JFET devices are wired in parallel, providing a 1/√2 noise voltage reduction that ends up making the discrete design even quieter. What you will notice with these noise plots is that with the bipolar devices, the noise curve approaches the ideal resistor noise line, that's the bold red line in the graph, at some point usually around 1000 to 2000 ohms, and then bends up and away from that line with increasing frequency. This is the result of the bipolar device, discrete or op-amp, noise current flowing through the source resistance, giving rise to an additional noise term that gets added to the voltage noise arising from the device-based spreader resistance. JFETs have no noise current mechanism and so do not diverge from the ideal resistor line, a noise line at HF. What can be said is that for discrete devices, the noise voltage of bipolar devices is generally lower than that of JFETs, and this of course makes them ideal candidates for moving coil amplifier stages where the source resistance is low enough not to give rise to any appreciable additional current noise times source resistance term. So in MC amplifiers, the main focus has to be on keeping the noise voltage to an absolute minimum. This plot is of the two LSK 389 devices wired in parallel and indicates that at 800 ohms and higher, the input referred noise is that of a pure resistance. In other words, there are no extraneous noise current terms, making it an ideal choice for a moving magnet preamplifier cartridge. The final design consideration we're going to look at is that of input overload capability. There have been some very expensive phono amps tested by John Atkinson of stereophile fame that have been shown to have very low overload margins, in one case just 9 dB. Before diving into the details here, let me explain a few things about this plot. Each of the dots you see is the peak stylus tip velocity in centimeters per second on the y-axis, plotted across frequency on the x-axis, and these figures are directly off the vinyl before equalization. I'll explain where those dots come from shortly. Most modern cartridges offer an output of 5 millivolts at 1 kHz, corresponding to 5 centimeters per second tip velocity at 1 kHz. So in this instance, you can read the peak tip velocity on the y-axis directly as millivolt output from the cartridge as well. Further, I added the green, red and purple traces to the plot. The green trace is the nominal RIAA preemphasis curve reference 5 centimeters per second in the midband, i.e. around 1 kHz, and is what the output response versus frequency looks like coming off the vinyl before any EQ. The red trace is the RIAA amplifier gain versus frequency response with the midband gain set to about 34 dB, a typical figure. The dotted purple trace is the output of the RIAA EQ amplifier given the notional 34 dB gain mentioned earlier. The red, green and purple traces can be read off directly in dB on the y-axis. To recap, the y-axis can be used to show the peak tip velocity, the millivolt output from the cartridge, assuming it generates 5 millivolts at 1 kHz at 5 centimeters per second stylus peak tip velocity, and finally in dB to show the gain and response of the input signal, RIAA UQ, and RIAA amplifier output. This graph and the recorded peak velocities, which are the dots that you see in that plot, is a result of work done in the mid-1970s to explore the dynamic range of phono-signals and was included in a paper on the subject by Tomlinson-Holman in 1976. What it shows is that reference to 5 centimeter per second peak stylus tip velocities at 1 kilohertz, many recordings showed peak values coming off the vinyl at 5 to 8 times this value, and in one case at 4 kilohertz, an astounding 70 centimeters per second, or plus 23 dB. To be sure, this is an outlier, but what is apparent is that in the mid-band, where the preamp gain is usually around 30 to 35 dB peak, velocities of 12 to 15 dB above the 1 kHz figure are quite normal. In this frequency region, we have a combination of plus 12 to plus 15 dB signal levels combined with a maximum or near maximum mid-band preamp gain. The RIAA amplifier EQ response drops off at minus 20 dB per decade above 2 kHz, but at 4 kHz that still leaves signal levels of 6 to 8 dB above this frequency while common, and plus 12 dB not out of the question in normal circumstances. Let's consider the figures we've just discussed a little differently. Starting out at 5 centimeters per second at 1 kHz, let's add 8 dB for peak signals in the 4 kHz region arising directly from the recording. I've used 8 dB here because at 4 kHz the amplifier gain will be 6 dB down on the 2 kHz gain. To this we should add plus 4 dB for hot recordings, i.e. records where the stylus excursions are the maximum physical displacement possible on vinyl. Many rock music vinyls would fall into this category. To this, add another 4 dB for high output or hot cartridges. This leaves us with an absolute minimum input overload of 16 dB. However, there's one final consideration, and that concerns clicks and pops. Although these are not RIA encoded, i.e. boosted at HF by the cutting amplifier, they nevertheless contain significant amounts of HF energy that can, if occurring simultaneously with peak music events, potentially cause overload. For this, add a further 3 dB, taking us to a total of 19 dB. Note that for active-passive designs that amplify the input signal first and then EQ it, you lose about 10 dB input overload at 4 kHz, and at 20 kHz the headroom loss is around 18 dB. However, it should also be noted that there's very little music energy much above 12 to 15 kHz, so overload at 20 kHz under these circumstances would be extremely rare. Following the work of a number of practitioners within the industry in the 1970s, considering the above factors, the minimum recommended overload figure of 25 centimeters per second was proposed, so about 14 dB. But in my view, and that of many other designers over the years, this is still skating on thin ice, and the majority of well-designed phonoamps are at 20 dB or better. Again, see some of the relevant reviews and comments by John Atkinson. Using an all-active topology on typical plus-minus 15-volt op-amp supply rails, figures of better than 20 dB are easily achievable. And on the X-Ultra MCMM, greater than 30 dB was achieved for both the MC and MM inputs. This table shows that if an MC cartridge is operated as a current transducer by feeding it into a virtual earth, despite the very low output voltages, considerable output current, i.e. tens of microamps, is available to drive a suitably configured load resistor across which to develop an output voltage. For the selection of MC cartridges shown in this table, the output currents range from just under 12 microamps for the Denon DL103, which is the cartridge I use, up to 57 microamps for the Autophon Contrapunt B. Some very esoteric devices like the AudioNode Condo feature 1 ohm coil resistances and 100 microvolt outputs, delivering even higher currents. This shows the basic, simplified circuit of how the MC front end works. The X-Ultra MC input stage treats the MC cartridge as a current transducer rather than a voltage output transducer, so the cartridge feeds into a very low resistance, 3.25 ohms, and the output from the transducer, output current from the transducer, is used as the input signal. The input current is the cartridge output voltage divided by the cartridge core resistance plus 3.25 ohms. In this type of circuit, called a transimpedance amplifier or current injection amplifier, the cartridge does not need any load resistors, and that's the reason there are no MC load resistor options on this preamplifier. The noise of the circuit is due to the input resistance of 3.25 ohms plus a small contribution from the power supply. The input signal current at A is replicated at the output B and flows through a load resistor R load, across which the output voltage of around 4 to 5 millivolts is developed. A little later we'll discuss the input servo. This servo adjusts the voltage at A to 0 microvolts plus minus 6 microvolts typical. I'm not going to go through the circuit diagram in detail component by component, since this is done in the Audio Express articles that you can download from the website. But what I'll do here is just cover a few points at block diagram level. The component references shown on the block diagram refer to the schematic diagram references. The MC and MM inputs come in via separate connectors at the rear of the unit, and the amplifier is arranged so that the output of the MC amplifier, if selected by push-button switch U25, feeds into the moving magnet amplifier RIAA EQ stage. This approach allowed each transducer input stage to be optimized for lowest noise, and is in contrast with many other designs that use the same input stage but simply up the gain for MC inputs. That approach almost always results in noise compromises, usually made on the MC input stage. The input voltage of the MC amplifier is served by U1, an ultra-low offset, low noise op-amp, so that the voltage at the MC signal input terminal is typically within plus minus 6 microvolts of ground at DC. This is done to ensure no excessive offset currents flow through the MC cartridge coil. The front-end plus minus 5 volt regulator for the MC input stage uses an LM4562 op-amp based regulator that features a total wideband noise of 7 nanovolts RMS, i.e. it is ultra quiet, with greater than 100 dB power supply ejection ratio at LF, and is still at 70 or 80 dB at 100 kHz. The MC front-end gain, as mentioned earlier, is set by adjusting the load resistor via dip switches at the rear of the unit, and will cover transducer currents of 10 microamps through to 60 microamps. Some people have asked me what happens if one or both of the input transistors go short on the MC preamp. I guess the concern here is that the preamp does go faulty. In this condition, it could fry an expensive $2,000 moving coil cartridge. If this happens, the worst case current through the coil would be 4 milliamps and more typically about 2.5 milliamps. In both cases, nowhere near enough to damage any MC cartridge. We'll now talk about the moving magnet phono stage that's shaded in green. The nominal 47K load can be reduced by switching an R79 and or R81 to allow cartridge inductance plus cable capacitance plus amplifier input capacitance caused peaking to be minimized. The front-end stage wires both devices in the LSK389 in parallel for a typical noise voltage density of 0.64 nanovolts per root hertz. The output of the first stage is coupled to an LM4562, so this is U26, through C90, a 2.2 microfarad film capacitor. This op-amp stage provides most of the loop gain. The RIAA feedback network couples from the output of U26 back to the front-end JFET source. The JFET drain current is set by the parallel combination of R74 and R75, which is 110 ohms. Although this 110 ohm resistance is a major source of noise in this amplifier with the input shorted, when a moving magnet cartridge is connected, the noise penalty is just 0.2 dB. You may ask why I did this. This is an all-active topology moving magnet phono amp, so the 0.2 dB noise penalty is a very small price to pay for the 30 dB overload margin this circuit features from 20 Hz to greater than 50 kHz. Further, by using a rather high value for the JFET source resistance, the equalization capacitance values are small and 1% NPO-COG types, easy to get and low cost. With a 500 millihenry plus 1300 ohm cartridge as a source, the signal-to-noise ratio reference 5 millivolts is 76.4 dB unweighted, which for a non-cooled input load resistor design such as this is within 0.6 dB of the theoretical maximum unweighted. The plus 10 volt regulator is similar in concept to the one used in the MC front end and uses the other half of U26 and features 7 nanovolts wideband noise or about 50 picovolts per root hertz spot noise. It is not possible to get 100% RIAA conformance with just a feedback network in an all-active topology EQ stage at the top end of the audio band. To accomplish this, a secondary low pass filter consisting of R58 and C63 is required. The RIAA conformance of this circuit is 0.15 dB, plus minus 0.15 dB, 20 Hz to 20 kHz, and it is still within 0.8 dB at 50 kHz. This is measured data. The last section we look at now is the system gain stage and the rumble filter, shaded in green. The system gain stage is built around U27 and OP1641 and allows the output of the preamp gain to be raised from circa 350 millivolts to 900 millivolts in approximately 3 dB steps. The gain setting switches are located at the rear of the unit. The rumble filter U17, also an OPA1641, is permanently in circuit and features a minus 40 dB per decade slope below 20 Hz. Via a push button at the rear of the unit, the turnover frequency can be raised to 45 Hz. I did this to allow the acoustic rumble evident in some classical recordings to be reduced. Although not shown in the block diagram, the power supply is a conventional plus minus 15 volt linear regulator based circuit fed from a Novatem Telema 3.2 VA PCB mounted toroid. The preamp includes a ground lifter consisting of two back-to-back MUR 820 200 amp peak current diodes. The ground lifter can be switched in or out with a switch at the rear of the unit. Note carefully, the ground lifter does not disconnect the preamp chassis from the incoming earth, aka safety ground, via the IEC mains power receptacle. It simply floats the X-Ultra MCMM electronics around the safety ground potential by about plus minus 0.6 volts and allows the X-Ultra MCMM preamp to assume the same ground potential as a line preamp that it would feed into. Towards the end of this video now, I just want to spend a few minutes talking about how the noise performance of the MCMM signal chain was verified using the Quantasylum QA401. I've taken the liberty here of tweaking the original diagram included in the Audio Express supplementary data to make it a little clearer. The one-to-one current translator shown here means that the input current going into A is translated to an output current appearing at B. The input current equaling the output current. This is a function, of course, of the MC complementary common base amplifier formed by Q1 and Q2 discussed earlier. Since the input to the MC head amp responds to current, the source and the amplifier input resistance of 3.25 ohm noise voltages must be converted to a noise current. To verify the equivalent referred to input thermal noise voltage, the calculated noise current at the MC head amp will be translated to a voltage at the output of the MC head amp appearing at B, and then amplified by the MMEQ amp by a fixed gain of 63 times or 36 dB. By comparing the calculated output noise with the measured noise at the preamplifier output using the QA401, the input noise floor of the MC head amp plus the MMEQ amplifier chain can be confirmed. In all the measurements, the QA401 measurement bandwidth was set to 192 kHz, 1.46 Hz FFT resolution with 50 averages, and the root Hertz mode selected. This is in the DBV menu tab on the QA401 PC screen. This latter setting simply normalizes noise readings to 1 Hz bandwidth so that the spot noise can be directly read off the monitor. Remembering that spot noise is just the noise measured over a 1 Hz bandwidth. To ensure a robust result, two measurements were done at the extremes of the MC head amp input resistance range. The first were the input at A shorted to ground through a 47 ohm resistor, and the second with the input A shorted directly to ground. The X-Ultra system gain in all measurements was set to 0 dB and the rumble filter to 20 Hz. In both measurements, the 1 kHz spot noise in figure 1 above was obtained by visual inspection directly from the Q401 display. With a 47 ohm resistor connected from the MC amplifier input to signal ground, the noise at the output V noise out was calculated at 603 nanovolts per root hertz, or minus 124.4 dBV. The measured result on the QA401 screen was 641 nanovolts per root hertz, a difference of 0.4 dB. The front-end gain in this measurement was about 9.9 times, and this was arrived at by taking the load resistance of 494 ohms and dividing that by 47 ohms plus 3.25 ohms. With the input of the MC amplifier shorted to ground, the output noise was calculated at 2.2 microvolts per root hertz, or minus 113 dBV. The measured spot noise was minus 112 dBV, so a difference of 1 dB. The front-end gain in this measurement setup was 152 times. Given the uncertainties of 1 dB in the QA401 visual noise reading due to display grass and 1% resistor component spreads, this is a good result from the measurement perspective and confirms the simulations and measurements are in agreement with each other in both cases. A few remarks here on the construction are in order. The preamp uses a standard Galaxy GX287 module shop housing measuring 230 millimeters wide by 170 millimeters deep with a 10 millimeter front plate. You have to drill 3 of 3.1 millimeter holes in the front plate for the indicator LEDs, but a template is provided in the build pack you can download on the Audio Express website. I had the brass nameplate you see here made at a local engraver's. The rear panel of the housing is replaced by a double-sided throw-plated PCB that is drilled, milled, screened, and gold flashed, so you don't have to fabricate one. As you can see, it's quite a complicated panel, but it looks extremely good once it's in place. The main board is a double-sided throw-plated silkscreen board and makes extensive use of SMD components, although the smallest size used is 0805. You can build one of these preamplifiers for about $350 to $400 all in, and the PCB sets are available at HiFiSonics.com for $49.50 plus $15 shipping. If you decide to build one of these, I can assure you will have an absolutely top-notch phono preamplifier that will serve you for years to come, no matter what your source. Don't forget to visit audioexpress.com to download the 2-part article, which was fully updated, including the BOM, which was fully updated in September 24, and other supplementary information. There's also a thread on DIYaudio.com in the analog source forum where you can get advice or help during assembly. Otherwise, just email me at bonsai@hifisonics.com. Thanks for watching. That's it. Hope you enjoyed the video, and if you like it, please give it a thumbs up. Thank you.